Well, thanks for attending, everybody. Let's see if I can keep you awake for about a half hour. So I was asked to talk about automotive issues, and I have a few concerns, and I thought I'd share those with you in the course of this presentation. Hopefully it seems relevant to you. You know, we can decide when a car was invented, but most people credit Carl Benz for coming up with this, motorized carriage back in 1886. And then along the way, Gordon Moore, Robert Noyce, they invented photolithography, and the first LSI chips came about 1958. The patent for Robert Noyce was 1958 for mass making. And so those two things are coming together. It kind of started, of course, the engine modules. The first thing I worked on, by the way, was an anti-skid device when I was at National years ago in the early 80s, probably late 70s. And we were working on an anti-skid device. It was a small analog device, and it was placed in BMWs and sold to Bosch. Bosch has continued to be a leader in automotive electronics. But really what drove it was electronics and automobiles was the EUCs, or the engine control modules, that were required as a part of the Clean Air Act. In other words, manufacturers needed to clean up their automobiles for smog, and they built these control modules, and those were initially inside the car in the glove compartment, but over time, through reliability was concerned as they moved them into the engine compartments. So reliability is a key issue as well in automotive electronics. So let's say basically it started in 1981. So there's three distinct phases, right, of automotive electronics. The first one was there were mechanical switches. For example, there's points in the distributor. The distributor sort of controls the spark of the that is relayed to the spark plugs that does the ignition of the car. Well, that preceded this. That was the mechanical replacement with electronic components. Next one, and this is where we are today, automotive assisted cars or assisted driver cars. And so you'll find things that, you're looking for cars in your lane, your nearest lane, so collision avoidance, for example, is something that we're seeing increasingly in cars today. What's going to come is the next thing. It's like automated, right? So some cars have it today, but an example of an automated capability is one that allows you to parallel park. Some cars have this already. I can tell you, I'll give you an example. So I get a new car every 3 years through a leasing program. So I get a Mercedes. And so in 2007, I paid $4,500 for the option to have the assisted parking, right? And collision avoidance was $2,500. So it's a lease car. I made some money, so I felt, well, heck, I'll just go ahead and get all the options. And so I grabbed all these options anyway. So fast forward, my next car, the collision avoidance was $1,200. That was in 2010. And the parallel parking was like $2,000. All right, fast forward to 2013, which is the last car I just got. And collision avoidance was $750. And the parallel parking they gave me for free in the package, right? No, well, as free as anything gets in the Mercedes. But, it actually, the cost of the car from 2007, this car, the same car, I always get the same SUV, an ML350. So the price of the car in 2007 was $102,000. The price in 2010 was $60,000, and the price in 2013 was $60,000. So not only are we getting better performance and safety with electronics, but we're really not seeing the price increase. So that's pretty amazing that works. And believe me, Mercedes isn't giving anything away. So if they're making lots of money on these things. But it's great that I got to tell you, probably as a result of getting older, I can tell you that collision avoidance system gets a lot of use. There's one autonomous feature that occurred too. It's like I was coming down 280. I was going to take 92, and I was probably on the phone. And I sort of pulled off on 92 to come across San Mateo to 101. And the darn thing braked for me. I never knew it could do that, but it sensed the car in front of me with its radar system and applied the brakes, and thus I avoided a collision. So I can tell you firsthand this stuff works, even if you know it's not, even if you don't know it's there. Okay, there's a lot of stuff here, but anyway, 50, 100, 150, 50 to 150 microcontrollers and processors in a car. If you do all the math, that's about $40 billion worth of automotive electronics that are out there. Now, these guys are predicting $240 billion business by 2020. This is why we all care about the automotive vertical, is because it's going to generate a lot of consumption of electronic components, specifically ICs, SoCs, and of course, things like boards and whatnot. A lot of software in these things too. We'll talk about that in a second. Anyway, so I think the costing functions for automotive electronics design, we've added a couple things that ordinarily we don't care about if we're designing a cell phone. Functionality we always care about. Performance we always care about. Cost we always care about. Those things have been around forever, right? So the two things that are really added is what quality, and quality means a couple different things with a car. Quality also means reliability, so that's quality and time. Resilience. So cars got to be in the field a long time. We'll see how long here in a second. And safety is a huge issue. This is a quick picture. You can just get an idea how many systems there are in a car now. It's amazing how many things there are. Often these systems, like for example, the system that does the differential, the automated differential, the sort of locking differential, it's the same system that does the brakes. So from a software standpoint, it's controlled and you get the behavior you want depending on the situation. The challenge is the verification of that, because sometimes the system will require it at the same time, thus the braking system is put at compromise occasionally. So these are very complicated systems to verify and validate. So we'll hear a lot of talk from the guys that are building emulation boxes over the course of the next couple of days, how they're focusing on automotive, because emulation is going to be key to the automotive verification of their electronic systems. Okay, so let's talk about some things, right? A couple quotes. So this guy Raj Nair, he's a guy responsible for most Ford's new products, and so you always see him at the trade shows. And he claims that it's got more code than a 777, which is an old platform by Boeing standards. So I went off and looked up how many lines of code in a 777. Well, there's 4 million lines of code in a 777. There's at least 150 computers, discrete computers and systems. Making it even worse is there's 79 different guys supplying the software. Think of that. If 79 guys try to write one software package, I don't know if I'd actually want to get in a 777 after I read this thing. Anyway, let's look at the cost. So the cheapest 777 you can buy from Boeing right now is $320.2 million. That gives you maybe 2 seats, and you can deliver mail in it or something. And so it's an incredibly expensive thing. By contrast, the Fusion he's talking about is $22,110. So it's got the same level of complexity in terms of the systems. It's got the same validation problem, yet it's 3 orders of magnitude cheaper. So these automotive guys are delivering a lot of value in their automotive electronics when compared with traditional electronic systems like planes. So let's look at this. This is a slide I got from Alan Labott. He's at Harvest. This is from last year. So you can see that automotive electronics is definitely increasing in terms of lines of code necessary to run a car. It's outpacing smartphones, and that makes sense because people aren't worried about safety in smartphones. You're not worried about reliability because everybody on the average gets a new phone every 2.5 years. So the average length of a car ownership is much longer. We'll talk about that. In terms of distribution of code, you can see a lot of it's in the radio, and then the powertrain's got, it's the orange, and I can't remember what EE is, but anyway, you can see there's a lot of code just in the informatics part of the car. So if you look at the performance and quality, the number one thing you got to worry about, I think, is that's really different between a cell phone and a car is, the fatality rate. So people getting wrecks. Anybody got teenagers? Anybody? Yeah. And I can tell you, I've had 3 teenagers, and I bought them each a car when they got about 16 because I got sick of driving them everywhere. And I can tell you, every one of them wrecked a car within a year. 100%. So my sample size is 3. I'm 3 for 3, right? Fortunately, they didn't kill themselves. They did cost me a little bit of money because of the car. So the numbers come way down, right? I mean, if you look back when before the Fed started mandating safety regulations, it was pretty high, right? So a lot of people died in car wrecks. Now, people are still not dying near as often, but still cars represent more deaths than heart attacks in the United States, which is a leading disease in terms of mortality. So cars are still pretty good place to get killed. So think about the liability. Think about what has to happen in terms of validation. So for this show, the automotive challenge is validation. Okay, that didn't line up very good. So I had a little glitch in my circle, but it's not a cell phone. I think this guy, Andrew Maynard, he said it pretty well. The implementation of complex in-car technology continues without a sophisticated understanding of the risk and benefits. Yeah, that's true. But I think the best part of this is that there's a bunch of unintended things or things you can't plan for. This is going to make this very, very difficult. So if you look at some of the people out there, how are they going to get coverage on their automotive electronics validation and verification? You can't use traditional methods. So this is going to be something where things like machine learning is going to be applied to this challenge and to ensure coverage. Okay, so one of the challenges is reliability. Cars are in the market a long time. The average new car is about 3.5 times longer than a smartphone. That places it at about 10 years. And so the thing that we don't often think about is it's just not the new car. Used cars stay in the market for another 5 years. So a typical car in the United States is going to be out there for 15 years. So in those 15 years, you got to have reliability. And sometimes the reliability comes in wear-out factors, but I think because it's so software intensive that there's just not things people think about. In a course of 15 years, especially from the time of design to the end of life of that car, there's going to be situations that were never anticipated when they were validated. So this is going to present a really big challenge in terms of the life of the car. That's something completely new for us. Okay, so what happens? Well, if we don't take care of this ourselves, the government often steps in and helps us. So in the automotive industry, we'll probably follow the path of what happened in the aerospace industry or the aeronautics industry. Probably actually will be regulated by DOT, Department of Transportation. There is some attempts initially to at least talk about functional safety in a spec. There's an ISO standard 26262. Wherever you go in here, you'll hear about how people are trying to comply with ISO standards. This is one they're complying with. But really, ISO doesn't tell you how to do it. It only tells you what you need. So the implementation is going to be very challenging, right? It's for everybody to have that done. So the manufacturers, the automotive manufacturers, by the way, here in the Valley, there's 25 automotive manufacturers. There's over 3,000 employees here in the Valley right now in terms of automotive stuff. So this, the peninsula, maybe Fremont if you count Tesla, is now becoming very intense in terms of automotive design for electronics. So if we don't take care of it, somebody else will. The government will step in and help us, as they always do. So where do we go from here? Okay. We just got to change our mindset. This is way different than an embedded systems problem in a cell phone or a smartphone. We got to really focus on safety and reliability. It's going to really demand a different kind of engineering discipline that we have. And of course, different kind of solutions that we're going to see from the likes of Synopsys, for example, right next to us, right? And it's got to go beyond just, understanding of the functional issue we're trying. It's also the time we have to start caring about the long-term effects of these things. And that'll be something that either makes us or breaks us. So the costing functions are going to be increased, right? For years, for as long as I've been doing this, we've been working about functionality is a key, validation concern. Performance always is, faster is always better, cheaper is always better, cost. We're adding two more things, quality, and specifically reliability and time. Quality and time or reliability, and lots about safety. We're going to have to add safety gates that we can't even imagine yet, right? There's going to have to be extended design in time, so you just don't design it, run it through simulation. You're going to get a lot of feedback from an alpha and beta cycle burning in cars. There's a reason car cycles take 6 years, so it's unlikely that we'll see shorter cycles in terms of new products in automotive, but it will increase our opportunity, or rather our challenge in terms of dealing with these things. And then, let's face it, we can't possibly find every problem. Hardware always has problems. And these things, we don't even know they exist yet, so they're not detected yet. They're unintended consequences of what we've been doing. Excuse me. So we're going to need to really keep our eyes open, try to rely on standards. It's going to require a lot of standards work, which is no fun, but necessary. And I think that's going to really consume a lot of time in terms of our ability to get the electronics design capability to these folks sooner. It may, in fact, retard the business a little bit. I can tell you that at the beginning of the electronics era, when we were doing engine modules, that took forever. The reliability thing was just out of our scope when I was working in semiconductor. And it probably took us a good 5 years to handle that. We probably don't have that much time. So the people that can deal with that will be the winners. The ones that can't will be the losers. Unfortunately, there will be some attrition associated with that. So when you think about the value stream, safety is going to be huge, as we're saying. Safety and quality is really going to be concerned. And process, what we're probably going to do, what we'll all have to do, is look to our suppliers, like the guys next door, like Cadence, for example, who's down at the other end, and look to them to help us solve this. They'll be big in the standards groups. They'll be people we can drive. We got to look to get that as part of our consumption. Now, not for this discussion, but for probably next year, we'll start talking about some of the challenges with autonomous automobiles. Autonomous automobiles will require altogether different things. If you think about it, if you have a plane has all this regulation, but it also has air traffic controllers. So you probably heard about smart streets, smart highways, things like that. Over the course of next year, we'll hear a lot of discussion like that. You can't have one without the other. You can't have autonomous cars without autonomous smart streets, smart highways. So, for example, in Sacramento, there's been at least 10 laws that have changed or been created as a result of these autonomous cars in the last year. So this is a field that is new to everybody, and it's just not going to be Google, as everybody knows. That's probably here at the show. Apple's building their own autonomous cars, and you see them running around Mountain View all the time. So it's just a matter of time. So next year we'll be talking about autonomous cars. Okay. So no one fell asleep, so that's cool.
Yep.
Oh, thanks.
Jim. Thank you so much. Any questions for Jim? But if you want to stick around for a second, we're going to be passing out. Yes, Charles.
Hey Jim, how much of this auto space though is going to be digital versus more analog because there's a ton of analog in this versus the a high performance SoC.
Yeah, you could extend that question to IoT too, right? So on the edge, where reality physics meets electronics, that's always analog. The sensors are always analog. So yeah, there's a fair amount of invention there, but it's mostly digital because it's all software controlled. So the software stack is just getting incredibly large, and the challenges to making that software work consistently, reliably, safety is going to be the challenge. So interesting enough, I suspect if we look at this show a couple years around, there's going to be a lot more emphasis on software tools. For example, the Coverity got bought by Synopsys last year. They bought a couple cybersecurity companies recently. So I think we'll see a lot more things about that. We were talking about, right before I came on, there was the Indy 500 in Indianapolis on Memorial Day. So one of the guys in the fan, wirelessly hacked into a race car and messed with the guy's brakes. So, because the Indy cars have a wireless module in their car that reports back to the pits, so about the performance of the car. So some guy in the stands hacked into the car while it was racing and altered the brakes. Not a really great thing when you're doing 200 miles an hour, right? So you can start to sense why Synopsys bought the cybersecurity company, right? Because it's going to be a big deal. So I know it's a long-winded explanation, but it's mostly digital, mostly software.